Picture this: every single thing you see, every color that reaches your eyes, every photon from distant stars that tells us about the cosmos, all travels at exactly the same speed. 299,792,458 meters per second. This isn't just a number, it's the speed limit of reality itself. When Albert Einstein made this speed central to physics over a century ago, he thought he was solving the puzzle of light. Instead, he opened a door to questions that still keep physicists awake at night. Because here's the thing, while we've defined this speed as a constant, measured it to incredible precision, and built our entire understanding of space and time around it, we still don't really know what it is. Is the speed of light a fundamental property woven into the fabric of reality itself? Or is it just a rule about how we measure things, like using a ruler made of rubber that stretches and shrinks? This isn't just academic curiosity. The speed of light defines everything. It determines what events can influence each other. It sets the boundaries of cause and effect. It tells us which parts of the universe we can ever hope to see. Think about it. Light from the most distant galaxies has been traveling toward us for over 13 billion years. That light carries information about the early universe, but it's limited by this cosmic speed limit. There are regions of space expanding away from us faster than light can travel toward us, regions we will never, ever see. The speed of light doesn't just illuminate our world, it defines the very edges of what we can know. But here's where it gets really strange. Throughout history, every time we thought we understood light's speed, reality threw us a curveball. Ancient philosophers assumed it was infinite. Then we discovered it was finite. We thought it was the same everywhere, then found it changes in different materials. We believed it was absolute. Then Einstein showed us it depends on who's measuring. And now, at the quantum level, we're discovering behaviors that challenge everything we thought we knew. The paradox is this: the more precisely we measure the speed of light, the more we realize we might be measuring something fundamentally different than what we think. Are we measuring a property of light itself? Or are we measuring the structure of space and time? Are we discovering a law of nature? Or are we just seeing the limits of our instruments? To understand why physicists today are still debating something that seems so settled, we need to journey back to the very beginning. Back to when humans first wondered about this invisible phenomenon that makes vision possible, and started the centuries-long quest to catch light in the act of moving. For thousands of years, humans looked up at the stars and assumed light traveled instantly across the cosmos. It seemed obvious. You open your eyes, you see. Lightning flashes, you see it immediately. The sun rises. Its light appears to reach Earth without delay. Even brilliant minds like Aristotle and Johannes Kepler believed light moved infinitely fast, arriving everywhere the moment it was created. This assumption made perfect sense to ancient philosophers. After all, they had no way to measure such incredible speeds. The fastest things they could observe were arrows, running horses, or falling stones. Nothing in their experience suggested that something as ethereal as light could have a measurable velocity. Light simply was, instantaneous and eternal, connecting the eye to the object in a single moment of perception. The ancient Greeks debated whether vision worked by light entering the eye or by the eye sending out rays to touch objects. But in both theories, the process was instantaneous. Empedocles proposed that Aphrodite lit a fire within the eye that reached out to illuminate objects. Euclid developed geometric theories of vision based on straight lines extending from the eye. But none of them imagined that light itself might take time to travel. Islamic scholars in the medieval period began to question some of these assumptions. Ibn al-Haytham, known in the West as Al-Hazen, conducted careful experiments with light and optics in the 11th century. He proved that light travels in straight lines and behaves predictably when reflected or refracted. but even his revolutionary work assumed that light moved infinitely fast. The idea that light had a finite speed was simply too radical to consider. This changed dramatically in 1676, when a Danish astronomer named Ole Rømer was doing something that seemed completely unrelated to the speed of light. He was working at the Paris Observatory, timing the eclipses of Io, one of Jupiter's 4 largest moons. As Io disappeared behind Jupiter and emerged again, Rømer was trying to create precise tables that would predict exactly when these eclipses would occur. But Rømer noticed something that puzzled him deeply. When Earth was moving toward Jupiter in its orbit, the eclipses happened slightly earlier than his calculations predicted. When Earth was moving away from Jupiter, they happened slightly later. The difference was small but consistent, about 16 minutes and 40 seconds over the course of Earth's entire orbit. At first, Rømer wondered if his instruments were faulty or if his calculations contained errors, but the pattern was too regular to be a mistake. Then he had an insight that would change physics forever. What if light wasn't instantaneous? What if it took time to cross the vast distance between Jupiter and Earth? Rømer realized that when Earth was at its closest approach to Jupiter, light from Io's eclipses had to travel about 4 astronomical units, less distance than when Earth was at its farthest point. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. If light took time to travel this extra distance, it would explain the timing differences he observed. By measuring the delay and knowing the extra distance light had to travel, Rømer calculated that light moved at about 214 million meters per second. His measurement was rough, and he was off by about 30% from the true value. But he had done something revolutionary. He had proved that light had a finite speed, and he had measured it across the solar system. Rømer's discovery sent shockwaves through the scientific community. The great Isaac Newton initially rejected the idea, as did many other prominent scientists. The notion that light could travel incredibly fast yet still have a finite speed seemed almost contradictory. How could something move so fast that it appeared instantaneous in everyday experience, yet still take measurable time to cross astronomical distances? But as more astronomers confirmed Rømer's observations, the evidence became undeniable. Light had a speed, and that speed was unimaginably fast, but not infinite. This discovery opened up entirely new questions about the nature of light itself. Was light made of particles that moved through space? Was it some kind of wave that propagated through a mysterious medium? And most intriguingly, could this speed be measured here on Earth? For nearly 2 more centuries, that last question seemed impossible to answer. Light moved so fast that any earthbound measurement appeared hopeless with the technology of the time. The fastest mechanical devices could barely keep up with sound, let alone something millions of times faster. Scientists needed to be incredibly clever about how they designed their experiments. In 1849, a French physicist named Hippolyte Fizeau decided to try something audacious. He set up an experiment using a rotating gear wheel with 720 teeth, each separated by gaps of equal width. He aimed a beam of light through one of the gaps toward a mirror positioned 8 kilometers away on a hilltop. The light would travel to the mirror, reflect back, and return to the gear wheel. Here's where Fizeau's genius showed. If the wheel was spinning slowly, the returning light would pass back through the same gap it had originally traveled through. But if the wheel was spinning fast enough, by the time the light returned, a tooth would have rotated into the position where the gap used to be, completely blocking the returning light. Fizeau spun his wheel faster and faster, watching the returning light grow dimmer as the teeth increasingly blocked the beam. At exactly 912 7/10 rotations per second, the returning light was completely blocked. At that precise rotation speed, he could calculate exactly how long the light took to make its round trip to the mirror and back. The math was straightforward, but required careful precision. In the time it took light to travel 16 kilometers, the wheel had rotated exactly far enough for one tooth to move into the position of the previous gap. Knowing the wheel's rotation speed and the spacing of the teeth, Fizeau calculated that light traveled at 315 million meters per second. Still not perfect, but much closer to what we know today, and achieved entirely with mechanical devices here on Earth. Just 1 year later, Léon Foucault improved dramatically on Fizeau's method, using a rotating mirror instead of a gear wheel. Foucault's setup was more precise and eliminated many sources of error that had affected Fizeau's measurement. His result was even more accurate, 298 million meters per second, remarkably close to the modern value. But it was Albert Michelson who turned measuring light speed into an obsessive art form. Starting in 1879 and continuing for over 50 years, Michelson dedicated much of his career to perfecting this single measurement. He used multiple mirrors arranged in complex geometric patterns, precisely controlled rotating mechanisms, and eventually measured distances between mountain peaks to create light paths dozens of kilometers long. Michelson's methods became incredibly sophisticated. He would set up one mirror on Mount Wilson in California and another on Mount San Antonio, 35 kilometers away. He used telephone lines to synchronize his equipment and compensated for atmospheric conditions that could affect the light's path. His measurements required him to know the distance between the mountains to within centimeters, leading to some of the most precise surveying work ever attempted. In 1926, Michelson conducted his most famous experiment in a 1.6 kilometer long vacuum tube to eliminate any effects from air. His final measurement in 1931, completed shortly before his death, was so accurate that it stood as the definitive value for decades: 299,792,458 meters per second, accurate to within a few meters per second. Then came 1905, and Albert Einstein changed everything with his special theory of relativity. Einstein didn't just say that light had a specific speed, he made a much more radical claim: that light's speed in a vacuum was exactly the same for all observers, regardless of how fast they were moving relative to the light source. This principle seemed to violate common sense. If you're in a car driving toward an oncoming vehicle, the relative speed between you and that vehicle is the sum of both your speeds. If you're driving away from a vehicle behind you, the relative speed is the difference between your speeds. But Einstein said that light behaved differently. Whether you're moving toward a light source or away from it, whether you're standing still or traveling at 99% the speed of light, you will always measure light moving at exactly the same speed. Einstein's insight meant that space and time themselves had to bend and stretch to keep light speed constant. If you're moving very fast toward a light source, time literally slows down for you, so that you still measure the same speed of light. If you're moving away from a light source, time speeds up. Distances contract and expand. The universe contorts itself to preserve this one fundamental constant. The speed of light became more than just the speed of light. It became the cosmic speed limit, the maximum velocity that anything with mass could approach but never reach. It became the conversion factor between mass and energy in Einstein's famous equation, E equals mc squared. It became the foundation upon which our entire understanding of space, time, and causality rests. By 1983, something remarkable and slightly circular happened. Scientists had become so confident in the constancy of light's speed and had measured it so precisely that they decided to stop measuring it altogether. Instead, they redefined the meter itself in terms of the speed of light and time, which could be measured even more precisely using atomic clocks. 1 meter became officially defined as the distance light travels in a vacuum in exactly 1,299,792,458th of a second. This created a strange situation where the speed of light became exactly 299,792,458 meters per second, not because we measured it to be that value, but because we defined it to be that value. Today, when scientists say they're measuring the speed of light, they're not really measuring it at all. They're using light to measure distances, or using distances to calibrate their equipment, because light speed is now a defined constant built into our system of measurement. The speed of light isn't a measured quantity anymore. It's a definition woven into the very fabric of how we quantify space and time. This seemingly final answer actually raises more questions than it resolves. If we've defined light's speed rather than measured it, how do we know it's really constant throughout the universe? How can we test something that we've made true by definition? What if the speed of light was different in the past, or varies in different regions of space? And most puzzling of all, why does this particular speed seem to govern so much more than just the motion of light itself? Here's something that might surprise you. The speed of light isn't always the speed of light. That famous number, 299,792,458 meters per second, only applies in one very specific situation: light traveling through perfect vacuum. The moment light encounters any kind of matter, everything changes. Walk into any room and look around. The light reaching your eyes from every object has been dramatically slowed down on its journey through air. Light in air travels about 99.97% the speed it would in vacuum. That might seem like a tiny difference, but it's enough to create mirages in the desert, make swimming pools look shallower than they really are, and cause stars to twinkle in the night sky. But air is nothing compared to what happens when light encounters denser materials. In water, light slows to about 75% its vacuum speed. In glass, it drops to roughly 67%. In diamond, one of the most optically dense materials we know, light crawls along at only 41% its maximum speed. These aren't small effects. Light in diamond is moving slower than light in glass by a factor of more than 1.5. This slowing happens because of something called the refractive index, a number that tells us how much a material bends and slows light. Vacuum has a refractive index of exactly 1, meaning light travels at its maximum speed. Air has a refractive index of about 1.0003. Water is 1.33. Glass ranges from 1.5 to 1.9 depending on its composition. Diamond clocks in at 2.42, meaning light in diamond travels at 1 divided by 2.42, or about 41%, its vacuum speed. But here's where things get really interesting. The refractive index isn't just a simple number. It depends on the color of light, the temperature of the material, the pressure it's under, and even the direction the light is traveling if the material has a crystal structure. This means that different colors of light travel at different speeds through the same material, causing white light to separate into rainbows when it passes through prisms or water droplets. This speed variation is why we see rainbows after rainstorms. White light from the sun contains all colors mixed together. When this light enters a water droplet, red light slows down less than blue light, because red light has a lower refractive index in water. The different speeds cause the colors to bend by different amounts, separating white light into its component colors. The rainbow isn't just beautiful, it's a demonstration that the speed of light depends on both the medium and the specific properties of the light itself. Even more strangely, scientists have found ways to slow light down to speeds that seem impossible. In ultra-cold clouds of atoms called Bose-Einstein condensates, researchers have slowed light pulses to less than 20 meters per second, slower than a bicycle. In some experiments, they've brought light to a complete stop, stored it for several seconds, and then released it to continue on its way. These aren't parlor tricks. They're demonstrations that our simple notion of light speed breaks down under extreme conditions. At the other extreme, scientists have created materials with negative refractive indices, metamaterials that bend light backwards, and can make objects appear invisible. In these materials, light still travels at finite speeds, but it behaves in ways that seem to violate our basic intuitions about how light should move through space. But even in perfect vacuum, light's apparent speed can vary in ways that challenge our understanding. This happens because massive objects like stars, planets, and black holes warp the fabric of space-time itself. Light always travels locally at the same speed, but the space through which it travels can be stretched, compressed, or twisted by gravity. Imagine light as a car driving on a highway. In flat space-time, it's like driving on a straight, level road at a constant speed. But gravity is like hills, valleys, and curves in the road. The car still travels at the same speed relative to the road surface, but an outside observer might see it take longer to reach its destination because the road itself is longer or more circuitous. This effect, predicted by Einstein's general theory of relativity, has been measured countless times. Light from distant stars takes longer to reach us when it passes close to the sun because the sun's gravity stretches the space through which the light travels. This is called the Shapiro delay, named after Erwin Shapiro, who first proposed measuring it in 1964. The delay is tiny for light grazing the sun, only about 200 microseconds. But it's been measured with incredible precision using radar signals bounced off planets and spacecraft. When Venus or Mercury passes behind the sun as seen from Earth, radio signals sent to spacecraft near those planets take measurably longer to return. The delay matches Einstein's predictions exactly. Near black holes, these effects become extreme. Close to the event horizon of a black hole, space is so warped that light following the shortest possible path between 2 points can take an arbitrarily long time to complete its journey as measured by a distant observer. Light can even orbit a black hole multiple times before escaping, following spiraling paths that would be impossible in flat space-time. This leads to one of the most mind-bending aspects of light's speed. Whether light appears fast or slow depends entirely on your reference frame. If you're falling into a black hole, you see light around you behaving normally. Every photon you encounter still passes you at exactly 299,792,458 meters per second. But an observer watching you fall from a safe distance sees your light signals becoming more and more delayed, stretched out over longer and longer periods of time. From the distant observer's perspective, light leaving you near the black hole appears to slow down, redshift to longer wavelengths, and eventually fade away entirely. But from your perspective, nothing unusual happens to light until the very moment you cross the event horizon. This isn't because light itself is changing speed. It's because the geometry of space-time near the black hole affects how different observers measure time and distance. These effects reveal something profound about the nature of light's speed. When we say light travels at a constant speed, we mean that any local observer, using local clocks and rulers, will always measure the same value. But observers in different gravitational fields or moving at different speeds can disagree about how long light takes to travel between distant points. This distinction between local and coordinate speeds becomes crucial when we consider the expansion of the universe itself. The most distant galaxies we can observe are moving away from us at speeds greater than the speed of light. This seems impossible if nothing can travel faster than light, but it's perfectly consistent with general relativity. The space between us and those distant galaxies is expanding, The galaxies themselves aren't moving through space faster than light, but the space containing them is stretching at such a rate that the distance between us and them grows faster than light could travel across it. Light from these galaxies can still reach us, but it takes longer and longer to make the journey as space continues to expand during the light's travel time. Some of the light we see today from the most distant galaxies was emitted when those galaxies were actually much closer to us than they are now. During the billions of years it took that light to reach us, the expansion of space has carried those galaxies much farther away. The light we're seeing is ancient, showing us what those galaxies looked like when the universe was much younger and smaller. This cosmic expansion creates another puzzle about light speed. If space itself is expanding and light has to travel through that expanding space, does the expansion affect light speed? The answer is subtle. Locally, light still travels at its standard speed through whatever medium it encounters. But globally, the expanding space stretches the wavelengths of light as it travels, causing distant objects to appear redshifted. This redshift isn't because the light is slowing down, it's because the space the light is traveling through is expanding during the light's journey. It's like trying to walk forward on a moving walkway that's stretching as you walk. Your walking speed relative to the walkway stays the same, but your progress relative to the terminal might be slower if the walkway is stretching faster than you can walk. These effects show us that our simple, everyday notion of speed breaks down when we consider the universe as a whole. Light doesn't just have one speed. It has different apparent speeds, depending on what it's traveling through, how gravity affects the space around it, and how we choose to measure time and distance. Even the vacuum of space isn't as empty as we once thought. Quantum mechanics tells us that empty space is filled with virtual particles constantly popping in and out of existence. These quantum fluctuations can affect light in subtle ways, potentially changing its speed by tiny amounts that we're only beginning to understand. The more we learn about light's behavior in extreme conditions, the more we realize that the speed of light isn't just a simple constant. It's a complex phenomenon that reveals deep truths about the nature of space, time, matter, and the fundamental structure of reality itself. What we call the speed of light might be better described as a speed limit built into the fabric of space-time. A limit that governs not just light, but the flow of information and the connection between cause and effect throughout the universe. This realization opens up even stranger possibilities. If light's speed can vary depending on circumstances we understand, might it also vary in ways we don't yet comprehend? Could the speed of light have been different in the early universe? Could it change over cosmic timescales? These questions push us into the realm of speculative physics, where established facts give way to bold theoretical possibilities. What if everything we think we know about the speed of light is wrong? What if that fundamental constant that defines reality itself isn't actually constant at all? This isn't science fiction speculation. It's a serious theoretical possibility that some physicists believe could solve some of the deepest mysteries in cosmology. The story begins with a problem that has puzzled cosmologists for decades: the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see something that shouldn't be possible according to standard cosmology. The temperature of this radiation is remarkably uniform across the entire sky, varying by only tiny fractions of a degree from one region to another. This uniformity seems impossible because different regions of the sky that we observe were never in contact with each other in the early universe. Light from opposite sides of the observable universe would not have had enough time to travel between these regions and equalize their temperatures. It's like finding that two separate pots of water, which have never been connected, have somehow reached exactly the same temperature. In standard cosmology, this is called the horizon problem because these regions lie beyond each other's causal horizons. They're so far apart that even traveling at the speed of light, no signal or influence could have passed between them in the time since the Big Bang. Yet somehow, they all ended up at almost exactly the same temperature. The mainstream solution to this problem is cosmic inflation, proposed by Alan Guth in 1981. Inflation theory suggests that the universe underwent a period of exponential expansion in its first tiny fraction of a second, growing faster than the speed of light. During this inflationary period, regions that are now separated by vast distances were once close enough to be in thermal contact. Inflation theory works mathematically and explains many observed features of our universe, but it requires some exotic physics. The inflationary expansion must be driven by a mysterious field called the inflaton, which has properties unlike anything we've ever observed. The field must start in a very specific state, undergo precisely the right kind of evolution, and then decay into the particles we observe today. This is where variable speed of light theories, or VSL theories, enter the picture. In the late 1990s, physicists like João Magalhães at Imperial College London and Andreas Albrecht at UC Davis proposed a radical alternative. What if, instead of space expanding faster than light, light itself traveled much faster in the early universe? The basic idea is surprisingly simple. If the speed of light was much higher in the very early universe, then regions that appear disconnected today could have been in causal contact when the universe was young. Light traveling at speeds trillions of times faster than today could have crossed vast distances and equalized temperatures across what would later become the entire observable universe. As the universe cooled and evolved, according to VSL theories, the speed of light gradually decreased to its present value. This isn't as crazy as it might sound. We already know that the speed of light in materials depends on the properties of those materials. VSL theories propose that the speed of light in vacuum depends on the properties of space-time itself, and those properties might have been very different in the extreme conditions of the early universe. João Magalhães, one of the leading proponents of VSL theories, describes the early universe as a place where the laws of physics themselves were still forming. In his book, Faster Than the Speed of Light, he argues that fundamental constants like the speed of light might not be truly constant over cosmic timescales. Instead, they might be dynamic quantities that evolved as the universe cooled from its initial state. VSL theories come in several different flavors, each proposing different mechanisms for how and why the speed of light might change. Some theories tie the speed of light to other fundamental constants, suggesting that as the universe expands and cools, multiple constants change together in coordinated ways. Others propose that the speed of light depends on energy density, so that in the extremely dense early universe, light could travel at arbitrarily high speeds. One of the most developed VSL theories is the bimetric model proposed by Magalhães and Albrecht. In this theory, there are actually two different metrics that describe the geometry of space-time. One metric governs the behavior of matter, while the other governs the behavior of light and other massless particles. In the early universe, these two metrics were very different, allowing light to travel faster relative to matter than it does today. Another approach, developed by John Barrow at Cambridge University, suggests that the speed of light varies smoothly over time, according to specific mathematical relationships. Barrow's models make precise predictions about how the speed of light should change and how this change should affect other observable quantities like the fine structure constant, which determines the strength of electromagnetic interactions. These aren't just abstract mathematical exercises. VSL theories make testable predictions that differ from those of inflation theory. For example, they predict different patterns in the cosmic microwave background radiation, different relationships between the densities of matter and energy in the universe, and different behaviors for the expansion rate of the universe over cosmic time. Some VSL theories also address another major cosmological puzzle, the flatness problem. Observations show that the geometry of space in our universe is remarkably close to perfectly flat. In standard cosmology, this flatness requires incredibly precise fine-tuning of initial conditions. The universe would have had to start with a density within 1 part in 10 to the 60th power of a critical value. Miss this target by even a tiny amount, and the universe would either collapse immediately or expand so fast that no structures could ever form. VSL theories can potentially solve the flatness problem without requiring such precise initial conditions. If the speed of light was much higher in the early universe, then the causal horizon was much larger, allowing physical processes to smooth out irregularities that would otherwise lead to curvature in spacetime. But VSL theories face significant challenges. Most fundamentally, they require us to abandon one of the most successful principles in modern physics, the idea that the laws of physics are the same everywhere and at all times. Einstein's theory of relativity is built on the assumption that the speed of light is a universal constant. If that assumption is wrong, then much of our understanding of space, time, and gravity might need to be revised. The experimental evidence for VSL theories remains inconclusive. Some studies have claimed to find variations in fundamental constants over cosmic time by analyzing light from distant quasars. But these results are controversial and have been challenged by other observations. The variations, if they exist at all, are tiny and at the edge of what current instruments can measure. One of the most careful studies was conducted by John Webb and his colleagues using the Very Large Telescope in Chile. They measured the fine structure constant in light from quasars billions of light years away, effectively looking back billions of years in time. Their initial results suggested that the fine structure constant was slightly smaller in the past, which would imply that fundamental constants do change over cosmic time. However, subsequent studies using different telescopes and analysis methods have failed to confirm these variations. Some studies even find evidence for variations in the opposite direction. The current consensus is that if fundamental constants do vary over cosmic time, the variations are so small that we cannot yet measure them reliably. VSL theories also face theoretical challenges. Changing the speed of light isn't as simple as just turning a dial. The speed of light is intimately connected to other fundamental constants and to the structure of electromagnetic theory itself. Changing it requires careful consideration of how all the other pieces of physics fit together. For example, the speed of light appears in Maxwell's equations, which describe electromagnetism. It also appears in the definition of the fine structure constant, which determines the strength of electromagnetic interactions. If the speed of light changes, then either these other quantities must change as well, or our understanding of electromagnetism must be modified in fundamental ways. Some VSL theories address these challenges by proposing that multiple constants change together in coordinated ways, preserving the mathematical structure of physical laws while allowing their numerical values to evolve. Others suggest that what we call fundamental constants are actually effective values that emerge from deeper, truly constant physics at the Planck scale. Despite these challenges, VSL theories continue to attract interest because they offer potential solutions to several major cosmological problems without requiring the exotic physics of inflation. They also raise profound questions about the nature of physical laws themselves. Are the constants of nature truly constant, or are they dynamic quantities that evolved along with the universe? Recent developments in string theory and quantum gravity have provided new contexts for VSL theories. In some string theory models, the speed of light and other fundamental constants are determined by the configuration of extra dimensions and the values of scalar fields that permeate spacetime. As the universe evolves, these fields could change, causing apparent constants to vary. The holographic principle, which suggests that the information in a volume of space can be encoded on its boundary, also provides new ways to think about VSL theories. If spacetime itself emerges from more fundamental information theoretic processes, then quantities like the speed of light, might be emergent properties that could vary under extreme conditions. Loop quantum gravity, another approach to quantum gravity, suggests that space-time has a granular structure at the Planck scale. In this framework, the speed of light might be an average property that emerges from the collective behavior of these discrete space-time units. Under extreme conditions, such as those in the early universe, this emergent speed might be very different from its present value. The debate between inflation and VSL theories reflects a deeper question about the nature of scientific explanation. Both theories can account for the observed uniformity of the cosmic microwave background, but they do so through very different mechanisms. Inflation preserves the constancy of physical laws while proposing exotic new physics. VSL theories avoid exotic physics while questioning the constancy of physical laws. This tension highlights one of the central challenges in modern cosmology. We're trying to understand the universe as a whole based on observations of light that has traveled billions of years to reach us. We're using physical laws derived from local experiments to explain phenomena that occurred under conditions vastly more extreme than anything we can reproduce in laboratories. VSL theories remain speculative, but they serve an important role in pushing the boundaries of our thinking about fundamental physics. They remind us that even our most basic assumptions about the nature of reality might be incomplete or incorrect. The speed of light, which seems so fundamental and unchanging in our everyday experience, might actually be a dynamic quantity that tells a story about the evolution of the universe itself. Whether VSL theories ultimately prove correct or not, they illustrate the ongoing vitality of theoretical physics. By questioning even the most fundamental assumptions, physicists continue to explore new possibilities for understanding the deepest mysteries of existence. The speed of light, whether constant or variable, remains a gateway to questions about the nature of space, time, and the laws that govern reality itself. Here's a strange fact about modern physics. We don't actually measure the speed of light anymore. Instead, we use the speed of light to measure everything else. This isn't just a subtle philosophical point. It's a fundamental shift in how science works that reveals something profound about the nature of measurement itself. To understand why this matters, we need to think carefully about what it means to measure anything. When you measure the length of a table with a ruler, you're comparing the table to a standard. The ruler is marked with units that are defined by some reference, traditionally a physical object kept in a vault somewhere. When you measure speed, you're comparing distance traveled to time elapsed, using standards for both distance and time. For most of history, this seemed straightforward. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. Later, it was redefined as the distance between two marks on a platinum iridium bar kept at the International Bureau of Weights and Measures in France. The second was defined as 1/86,400th of a mean solar day. With these definitions, measuring the speed of light meant carefully measuring how far light traveled in a precisely measured amount of time. But by the mid-20th century, scientists realized they could measure time much more accurately than they could measure distance. Atomic clocks, which count the oscillations of atoms as they absorb and emit energy, could measure time to incredible precision. By 1967, the second was redefined in terms of atomic vibrations. Exactly 9,192,631,770 oscillations of a cesium-133 atom. Meanwhile, the speed of light had been measured with increasing precision using these ultra-accurate clocks. Scientists realized that they could measure the speed of light more accurately than they could measure the standard meter bar. This led to a revolutionary decision in 1983. Instead of using the meter to help define the speed of light, they used the speed of light to define the meter. The new definition was elegantly simple. 1 meter is the distance light travels in vacuum in exactly 1,299,792,458 of a second. This made the speed of light exactly 299,792,458 meters per second. Not because we measured it to be that value, but because we defined it to be that value. This created what philosophers of science call a circular definition. We define distance in terms of light speed and time. We define light speed in terms of distance and time. The circle is closed, and we can't step outside it to independently verify that light really travels at the speed we say it does. But this circularity isn't a flaw in our measurement system, it's a feature. It reflects a deep truth about how measurement works in modern physics. All measurement is ultimately based on comparing one thing to another. There's no absolute reference point, no view from nowhere that allows us to measure things independently of our measurement standards. Consider how we actually measure distances today. We don't use meter sticks or surveying chains. We use laser interferometry, radar ranging, or GPS satellites. All of these methods fundamentally depend on timing light signals. When GPS calculates your position, it measures how long radio waves take to travel from satellites to your receiver. When scientists measure the distance to the moon, they bounce laser beams off reflectors left by Apollo astronauts and time how long the light takes to return. This means that every precise distance measurement we make automatically assumes that light travels at exactly the speed we've defined it to have. We can't use these measurements to test whether the speed of light is really constant, because constancy is built into our definition of distance itself. The same circularity appears when we try to measure the speed of light directly. Modern experiments use laser interferometers, devices that split a laser beam, send the two halves along different paths, and then recombine them to create interference patterns. By measuring tiny changes in these patterns, scientists can detect incredibly small changes in the lengths of the paths. But here's the catch. Interpreting these interference patterns requires us to know the wavelength of the laser light we're using. And the wavelength depends on both the frequency of the light and its speed. We measure frequency very accurately using atomic clocks, but to convert frequency to wavelength, we need to know the speed of light. Once again, we're using the speed of light to measure the speed of light. This circularity becomes even more apparent when we consider how GPS works. The global positioning system relies on incredibly precise timing to determine locations. Each GPS satellite carries atomic clocks and broadcasts time-stamped signals. Your GPS receiver compares the arrival times of signals from multiple satellites to calculate your position. But GPS wouldn't work without Einstein's theory of relativity. The satellites are moving at high speeds relative to Earth, which causes their clocks to run slightly fast due to special relativistic time dilation. They're also higher in Earth's gravitational field, which causes their clocks to run slightly slow due to general relativistic gravitational time dilation. The net effect is that satellite clocks gain about 38 microseconds per day compared to clocks on Earth's surface. This might seem like a tiny error, but it would cause GPS positions to drift by about 10 kilometers per day if not corrected. GPS works only because we understand how the speed of light, time, and gravity interact according to Einstein's theories. We use these theories to correct the satellite clock readings, and then use the corrected times to calculate distances based on light travel times. The circular logic is inescapable. We use Einstein's theories, which assume the speed of light is constant, to correct our clocks. We use these corrected clocks to measure distances by timing light signals. We use these distance measurements to test Einstein's theories, which confirm that the speed of light is constant. Every step in the process assumes what we're trying to verify. This same circularity appears in gravitational wave detection. The Laser Interferometer. Gravitational Wave Observatory, LIGO, detects gravitational waves by measuring incredibly tiny changes in the lengths of its 4-kilometer-long arms. When a gravitational wave passes through LIGO, it stretches space in one direction and compresses it in the perpendicular direction by amounts smaller than 1/10,000th the width of a proton. LIGO detects these changes using laser interferometry. Laser light travels down each arm, reflects off mirrors, and returns to create interference patterns. Changes in arm length cause changes in these patterns that can be measured with extraordinary precision. But interpreting these measurements requires us to assume that light travels at a constant speed in vacuum, even as space itself is being stretched and compressed by passing gravitational waves. The first gravitational wave detection, announced in 2016, was hailed as a spectacular confirmation of Einstein's general theory of relativity. But the detection relied completely on assuming that Einstein's theory correctly describes how light behaves in curved spacetime. We used Einstein's predictions about light to build the detector, used Einstein's equations to interpret the signals, and then concluded that Einstein was right about gravitational waves. This isn't fraud or sloppy science. It's how science necessarily works when we're probing the fundamental structure of reality. We can't step outside the universe to measure it with independent tools. We have to use parts of the universe to measure other parts, and this inevitably creates logical loops and circular dependencies. The circularity becomes even more profound when we consider quantum mechanics. In quantum field theory, the speed of light isn't just the speed at which light travels. It's a fundamental parameter that determines the structure of space-time itself. It sets the conversion factor between space and time coordinates, determines the maximum speed at which information can travel, and governs the relationship between energy and momentum for all particles. Quantum electrodynamics, our most precise theory of electromagnetic phenomena, predicts the behavior of light and matter with incredible accuracy. The theory's predictions for quantities like the magnetic moment of the electron agree with experiments to 12 decimal places. But these calculations all assume that the speed of light has exactly the value we've assigned to it by definition. When we test quantum electrodynamics by measuring properties of electrons or photons, we're testing a theory that assumes a specific value for the speed of light. When the theory's predictions match our measurements, we conclude that the theory is correct, including its assumption about the speed of light. But we couldn't have made the measurements without already assuming that light behaves according to the theory we're testing. Modern particle physics experiments push this circularity to extremes. At the Large Hadron Collider, scientists accelerate protons to 99.999991%, the speed of light, and smash them together to create exotic particles. The entire analysis of these collisions depends on Einstein's theory of special relativity, which assumes that the speed of light is the ultimate speed limit. The detectors themselves rely on light signals to track particles. When a high-energy particle passes through the detector, it creates flashes of light, electrical signals, or other electromagnetic disturbances that travel at the speed of light to recording equipment. The timing and positions of these signals are used to reconstruct the paths and properties of the original particles. But interpreting these signals requires precise knowledge of how light behaves in the detector materials, how electromagnetic signals propagate through the electronics, and how relativistic effects modify particle trajectories. All of these calculations assume that the speed of light is exactly what we've defined it to be. The circular logic extends to our most distant observations. When astronomers measure the distances to far galaxies using type Ia supernovae, they're using the fact that these stellar explosions have known intrinsic brightness. By comparing the apparent brightness to the intrinsic brightness, they can calculate how far away the supernova is. But this calculation assumes that light from the supernova travels through space at a constant speed. If the speed of light varied over cosmic time or distance, it would affect both the light travel time and the apparent brightness in ways that could mimic other effects. The discovery that the universe's expansion is accelerating, which led to the concept of dark energy, relies entirely on assuming that light from distant supernovae behaves exactly as our theories predict. Even our most fundamental calibrations involve circular reasoning. The meter is defined using the speed of light, but we calibrate our frequency standards using atomic transitions whose energies are calculated using quantum mechanics. Quantum mechanics predicts these energies using fundamental constants, including the speed of light. We use these predictions to build better atomic clocks, which we use to make more precise measurements of the speed of light, which confirms our quantum mechanical calculations. This isn't a problem that better technology can solve. It's a fundamental feature of how measurement works when we're trying to understand the basic laws of physics. We can't measure the fundamental constants of nature independently because they're all interconnected. Changing one requires changing others in coordinated ways to preserve the mathematical consistency of our theories. The circularity does have an escape hatch, but it's a narrow one. If we ever discovered that our measurements were inconsistent with each other in ways that couldn't be explained by experimental error, it might indicate that our assumptions about fundamental constants were wrong. For example, if GPS satellites gained different amounts of time than Einstein's theory predicted, or if LIGO detected gravitational waves with the wrong polarization, it might suggest that the speed of light wasn't really constant. But such discoveries would be incredibly difficult to interpret. Any inconsistency could be explained by unknown systematic errors, incomplete understanding of the experimental conditions, or effects from new physics that we haven't discovered yet. Distinguishing between these possibilities would require careful analysis and probably multiple independent confirmation experiments. The circular nature of fundamental measurements reflects something profound about the relationship between observation and theory in modern physics. We don't simply observe the world and then construct theories to explain what we see. Instead, our theories and our observations are intimately intertwined. Our theories tell us how to build instruments, how to interpret measurements, and what patterns to look for in data. Our observations test our theories, but only within the framework that the theories themselves provide. This circularity isn't a weakness of science, it's a strength. It shows that our theories form coherent, self-consistent frameworks for understanding reality. The speed of light isn't just an isolated fact about light, it's part of a vast web of interconnected concepts that includes space, time, energy, momentum, gravity, and electromagnetism. The remarkable thing isn't that these concepts are circular, it's that they fit together so precisely and make such accurate predictions about the natural world. At the quantum level, light becomes something far stranger than anything Newton, Maxwell, or even Einstein could have imagined. It's not just a wave rippling through space or a stream of particles flying through vacuum. It's something that seems to exist in multiple states simultaneously, something that can be in two places at once, something that appears to know about events before they happen. And yet, through all this quantum weirdness, light still respects that fundamental speed limit of 299,792,458 meters per second. The quantum nature of light was discovered accidentally in 1900, when Max Planck was trying to solve a seemingly simple problem. Why do hot objects glow the colors they do? Classical physics predicted that a perfectly hot object should emit infinite energy at high frequencies. A prediction so absurd it was called the ultraviolet catastrophe. Planck solved the problem by proposing that energy comes in discrete packets, or quanta, rather than continuous amounts. Planck's solution worked mathematically, but he didn't really believe that energy was actually quantized. He thought it was just a mathematical trick that would eventually be explained by more fundamental classical physics. But Albert Einstein took Planck's idea seriously and used it to explain another puzzle, the photoelectric effect. where light shining on certain metals causes them to emit electrons. Einstein proposed that light itself comes in discrete packets of energy called photons. Each photon carries energy proportional to its frequency, with the proportionality constant being Planck's constant. This meant that light wasn't just a wave, as Maxwell's equation suggested, but also behaved like a stream of particles. Low-frequency light like radio waves consists of photons with very little energy each. High-frequency light like X-rays consists of photons with enormous energy each. But here's where quantum mechanics becomes truly bizarre. These photons aren't like classical particles. They don't have definite positions or definite paths through space. Instead, they exist as probability waves that describe the likelihood of finding the photon at any particular location if you measure it. The wave nature and particle nature aren't separate aspects of light. They're different ways the same quantum phenomenon appears depending on how you observe it. This wave-particle duality leads to some of the most counterintuitive experiments in physics. In the famous double-slit experiment, individual photons are fired one at a time toward a barrier with two parallel slits. If you think of photons as particles, each one should go through either the left slit or the right slit and hit the screen behind the barrier in one of two regions. But that's not what happens. Instead, the photons create an interference pattern on the screen, with alternating bright and dark bands, just like you'd expect from waves passing through both slits simultaneously. Somehow, each individual photon seems to go through both slits at the same time and interfere with itself. Even stranger, if you try to determine which slit each photon actually goes through by placing detectors at the slits, the interference pattern disappears. The act of measurement seems to force each photon to choose a definite path, destroying the wave-like behavior that creates the interference pattern. The photons somehow know whether you're watching them and change their behavior accordingly. This isn't just a quirk of how we detect light. It reveals something fundamental about the nature of reality at the quantum scale. Before measurement, quantum systems exist in superpositions of multiple states simultaneously. The photon really is going through both slits at the same time until the moment you measure it and force it to collapse into a definite state. What makes this even more mysterious is that photons always travel at exactly the speed of light, regardless of their energy. A low-energy radio wave photon and a high-energy gamma-ray photon both move through vacuum at precisely the same speed. This is completely different from classical particles, where more energetic particles typically move faster. Photons seem to have only one speed setting, maximum. This constant speed emerges from a deeper quantum mechanical principle. Photons are massless particles, and Einstein's theory of special relativity says that any massless particle must always travel at the speed of light. It can't speed up, slow down, or stop. From the moment a photon is created until the moment it's absorbed, it moves at exactly 299,792,458 meters per second. But quantum mechanics adds layers of weirdness to this picture. Photons don't follow definite paths through space like classical particles. Instead, they follow all possible paths simultaneously, with each path contributing to the total probability of the photon reaching its destination. This is the basis of Richard Feynman's path integral formulation of quantum mechanics, which describes particles as simultaneously exploring every conceivable route between 2 points. In Feynman's picture, a photon traveling from point A to point B doesn't just take the straight line path that classical physics would predict. It also takes curved paths, zigzag paths, paths that loop around several times, and even paths that seem to go backwards in time before arriving at their destination. All of these paths contribute to the quantum mechanical calculation of where the photon is likely to end up. Most of these alternative paths cancel each other out due to quantum interference, leaving only the classical straight-line path as the most probable. But in certain circumstances, some of the alternative paths can become important, leading to quantum effects that have no classical analog. This is why quantum mechanics reduces to classical physics in most everyday situations, but produces bizarre behavior under carefully controlled conditions. The quantum nature of light becomes even stranger when we consider virtual particles. In quantum field theory, empty space isn't really empty. It's filled with virtual photons and other virtual particles that constantly pop in and out of existence due to quantum fluctuations. These virtual particles exist for such short times that they can't be directly detected, but they have measurable effects on the behavior of real particles. Virtual photons are responsible for all electromagnetic forces. When two electrons repel each other, they do so by exchanging virtual photons. When an atomic nucleus holds electrons in orbit, it does so through virtual photon exchanges. Every electromagnetic interaction, from the force that holds atoms together to the radiation from distant stars, can be described as an exchange of virtual photons between charged particles. These virtual photons don't always respect the speed of light in the same way that real photons do. In quantum field theory, virtual particles can have energies and momenta that would be impossible for real particles. They can appear to travel faster than light, exist with negative energy, or violate conservation laws in ways that would be forbidden for observable particles. But this apparent violation of the speed of light limit doesn't allow faster than light communication or travel. Virtual particles can't carry information between distant locations because they can't be directly observed or controlled. They're mathematical artifacts that arise from the quantum mechanical description of fields, not physical objects that could be used to send signals. The distinction between virtual and real particles illustrates one of the deepest aspects of quantum mechanics: the role of observation in determining what's real. Virtual particles exist only in the calculations that describe quantum processes. They're useful mathematical tools that give correct predictions for experimental results, but they don't correspond to anything you could directly measure or interact with. Real photons, by contrast, can be detected, counted, and manipulated. They carry definite amounts of energy and momentum, and they always travel at the speed of light. But even real photons have quantum properties that challenge our classical intuitions about reality. For example, photons can be entangled with each other in ways that seem to allow instantaneous communication across arbitrary distances. When two photons are entangled, measuring the properties of one photon instantly determines the properties of the other, even if they're separated by light years. Einstein famously called this spooky action at a distance because it seemed to violate the principle that nothing can travel faster than light. But quantum entanglement doesn't actually allow faster than light communication. You can't use entangled photons to send information because the measurement results on each photon appear random. Only when you compare the results from both photons do you see the correlations that reveal the entanglement. This comparison requires classical communication, which is limited by the speed of light. The quantum properties of light have practical applications that are becoming increasingly important in modern technology. Quantum cryptography uses the quantum properties of photons to create unbreakable codes. Any attempt to eavesdrop on a quantum encrypted message necessarily disturbs the quantum states of the photons, revealing the presence of the eavesdropper. Quantum computing promises to use the quantum properties of photons and other particles to perform certain calculations exponentially faster than classical computers. Photons are particularly useful for quantum computing because they can maintain their quantum properties over long distances and are relatively immune to environmental interference. But these quantum technologies still respect the fundamental speed limit imposed by the speed of light. Quantum computers can't solve problems faster by sending information faster than light. They gain their advantage by exploring multiple solutions simultaneously through quantum superposition. not by communicating faster than classical physics allows. The quantum nature of light also reveals new aspects of the speed of light itself. In quantum electrodynamics, the most precise theory of electromagnetic phenomena, the speed of light emerges from the underlying structure of quantum fields. It's not just the speed at which photons happen to travel, it's a fundamental parameter that determines how space and time are related at the deepest level. The speed of light appears in the commutation relations that define how quantum fields behave at different points in space-time. These relations ensure that measurements made at locations separated by space-like intervals can't influence each other, preserving the causal structure that prevents faster than light signaling. The speed of light isn't just a speed limit for particles, it's the speed limit for causality itself. This connection between the speed of light and the structure of space-time becomes even more apparent in quantum field theory in curved space-time. When quantum fields interact with gravity, the local speed of light can appear to vary due to the curvature of space-time. But this variation preserves the fundamental quantum mechanical relationships that prevent faster than light communication. Recent experiments have pushed our understanding of quantum light to new extremes. Scientists have created single photon sources that emit exactly one photon at a time, allowing unprecedented control over quantum states of light. They've demonstrated quantum teleportation, where the quantum state of one photon is transferred to another photon at a distant location without the photons themselves traveling between the locations. These experiments reveal that the quantum nature of light is even stranger than early quantum physicists imagined. Light can exist in squeezed states where some properties are measured more precisely than quantum mechanics normally allows, at the cost of making other properties more uncertain. Light can be put into cat states where it exists in superpositions of vastly different energies simultaneously. But through all of these quantum manipulations, light still travels at exactly the same speed. No matter how we prepare photons, how we entangle them, or how we measure them, they still move through vacuum at 299,792,458 meters per second. The quantum weirdness of light doesn't change its speed. It reveals new aspects of what speed means in a quantum universe. This constancy of light speed in quantum mechanics points to something profound about the nature of physical law. The speed of light isn't just an empirical fact about how fast light happens to move. It's a structural feature of reality that determines how space, time, matter, and information are related. Quantum mechanics doesn't violate this structure, it reveals its deeper implications. The quantum nature of light also suggests new questions about the meaning of the speed of light. If photons don't follow definite paths through space, what does it mean to say they travel at a definite speed? If virtual photons can appear to move faster than light, what distinguishes the speed limit for real particles? If entangled photons can influence each other instantaneously, what preserves the causality that the speed of light is supposed to protect? These questions push us toward even deeper theories that attempt to unify quantum mechanics with gravity and explain the ultimate nature of space and time. In these theories, the speed of light might emerge from more fundamental processes, just as the properties of matter emerge from the quantum interactions of atoms and molecules. Understanding these deeper processes might finally reveal why light travels at the speed it does, and whether that speed is truly fundamental or just another emergent property of a more basic underlying reality. What if the speed of light isn't really fundamental at all? What if it's like the speed of sound in air, an emergent property that arises from deeper, more basic processes? This question strikes at the heart of our understanding of reality itself, challenging the assumption that the constants we observe in nature represent the deepest level of physical law. The speed of sound provides a useful analogy for thinking about this possibility. Sound waves in air travel at about 343 meters per second at room temperature. This speed emerges from the properties of air molecules, their mass, the forces between them, and how densely they're packed together. Sound isn't a fundamental phenomenon, it's a collective behavior that emerges when millions of molecules coordinate their motion in wave-like patterns. If you didn't know about atoms and molecules, you might think the speed of sound was a fundamental constant of nature. You could measure it precisely, build theories around it, and use it to understand acoustic phenomena. But once you understand that air is made of discrete particles, you realize that the speed of sound is just an effective property that emerges from more basic physics. Could the speed of light be similar? Could it emerge from the collective behavior of more fundamental entities, just as sound emerges from the motion of molecules? This possibility has profound implications for physics, suggesting that space and time themselves might not be fundamental, but might arise from deeper information, theoretic or quantum mechanical processes. The idea gains credibility from our understanding of how other apparently fundamental quantities turn out to be emergent. Temperature, for example, seems like a basic property of matter until you realize it's actually a measure of the average kinetic energy of atoms and molecules. Pressure emerges from countless molecular collisions with container walls. Even apparently solid matter emerges from quantum mechanical interactions between electrons and atomic nuclei. In the early 20th century, physicists discovered that many properties of materials could be understood as emergent phenomena arising from atomic structure. The hardness of diamond, the conductivity of metals, the transparency of glass, all emerge from quantum mechanical interactions between electrons and atoms. None of these properties exist at the level of individual particles. They only appear when large numbers of particles interact in organized ways. Modern condensed matter physics has pushed this understanding much further, revealing that even more exotic phenomena can emerge from simple underlying rules. Superconductivity emerges when electrons pair up and move through materials without resistance. Superfluidity emerges when atoms cool to such low temperatures that they all occupy the same quantum state. These phenomena have no analog in the behavior of individual particles. They're purely collective effects. Some of the most striking examples come from analog models of gravity and cosmology. Researchers have created systems where sound waves in flowing fluids behave exactly like light in curved space-time. In these acoustic black hole analogs, the speed of sound plays the same role that the speed of light plays in Einstein's theory of general relativity. In a flowing fluid, sound waves can't escape from regions where the fluid flows faster than the local speed of sound, just as light can't escape from regions where space curves more severely than light can traverse. The boundary where escape becomes impossible is called an acoustic horizon, and it behaves remarkably like the event horizon of a real black hole. These analog systems demonstrate that phenomena we associate with fundamental physics can emerge from completely different underlying mechanisms. The analog black holes obey the same mathematical relationships as real black holes, including Stephen Hawking's prediction that black holes should emit thermal radiation. But in the analog systems, this Hawking radiation emerges from the quantum properties of the fluid, not from the curvature of space-time. If such complex gravitational phenomena can emerge from fluid dynamics, might real gravity and the speed of light also emerge from more fundamental processes? Some theoretical physicists think the answer is yes, and they're exploring models where space-time itself emerges from quantum information or other more basic substrates. One of the most influential ideas along these lines is the holographic principle, which suggests that all the information in a volume of space can be encoded on the volume's boundary. This principle arose from studying black holes, where physicists discovered that the amount of information a black hole can contain is proportional to the area of its surface, not its volume as you might expect. The holographic principle implies that what we experience as three-dimensional space might actually be a projection of information stored on a two-dimensional surface, like a hologram. In this view, the speed of light might not be a fundamental property of space, but rather an emergent feature of how information is processed and transmitted in the holographic encoding. String theory, one of the leading candidates for a theory of quantum gravity, also suggests that the speed of light might be emergent. In string theory, the fundamental entities are one-dimensional strings rather than point particles. These strings can vibrate in different patterns, and different vibration modes correspond to different particles, including photons. The speed at which disturbances propagate along these strings depends on the tension in the strings and the geometry of the extra dimensions in which they vibrate. In principle, different regions of the higher dimensional space could have different string tensions, leading to different effective speeds of light in different regions of our three-dimensional space. Some string theory models predict that what we call fundamental constants, including the speed of light, are actually determined by the sizes and shapes of extra dimensions that are curled up too small for us to detect directly. As the universe evolves, these extra dimensions could change size or shape, causing the apparent constants to vary over cosmic time. Loop quantum gravity, another approach to quantum gravity, suggests a different mechanism for the emergence of the speed of light. In this theory, space itself has a granular structure at the Planck scale, with discrete units of area and volume that can't be subdivided further. The speed of light might emerge as an average property, describing how information propagates across this granular space-time. Think of it like pixels on a computer screen. From a distance, the screen appears to show smooth curves and continuous motion. But zoom in far enough, and you see that everything is made of discrete pixels. The apparent smoothness emerges from the collective behavior of many pixels, each of which can only be in one of a finite number of states. Similarly, the smooth space-time of Einstein's general relativity might emerge from the collective behavior of discrete space-time units. The speed of light would then be like the refresh rate of the cosmic computer, determining how quickly information can propagate from one space-time pixel to its neighbors. This granular view of space-time makes specific predictions about how light should behave under extreme conditions. If space-time really is discrete at the Planck scale, then very high-energy photons might experience tiny delays compared to lower-energy photons, as they interact differently with the granular structure. Several experiments are searching for such effects in gamma-ray bursts from distant astronomical objects. The emergence scenario becomes even more intriguing when we consider the possibility that space-time itself might be emergent from quantum entanglement. Recent research in quantum information theory suggests that the geometric properties of space-time, including the relationships that determine light speed, might arise from the entanglement structure of quantum fields. In this picture, space emerges when quantum systems become entangled in specific patterns. The more entangled two regions are, the closer they appear in the emergent space-time. The speed of light then becomes a measure of how quickly entanglement relationships can change, setting a fundamental limit on information processing rather than motion through space. This connection between entanglement and space-time is more than just speculation. Physicists have demonstrated that the entropy of entanglement in quantum field theories is directly related to the areas of surfaces in the corresponding space-time geometries. This relationship, known as the Ryu-Takayanagi correspondence, provides a concrete mathematical link between quantum information and space-time geometry. If space-time emerges from entanglement, then the speed of light might not be fundamental, but might instead reflect the underlying information processing capabilities of quantum systems. Just as the speed of sound in a material depends on the mechanical properties of atoms and molecules, the speed of light might depend on the information theoretic properties of whatever quantum substrate gives rise to space-time. This perspective suggests new ways to think about violations of the speed of light limit. In emergent theories, the speed limit might not be absolute, but might depend on the energy scale or the specific conditions under which space-time emerges. At extremely high energies, approaching the Planck scale, the emergent description might break down, potentially allowing for apparent faster-than-light phenomena. Some theories propose that the speed of light might have been different in the early universe, when energy densities were much higher, and the conditions for space-time emergence were very different from today. As the universe cooled and the emergent space-time structure stabilized, the speed of light might have approached its current value. These ideas are still highly speculative, but they're beginning to make contact with observable phenomena. The recent detection of gravitational waves has opened a new window into the nature of space-time, allowing us to test theories of emergence under conditions of extreme curvature and high energy density. Future experiments might be able to detect signatures of space-time granularity or other emergent phenomena. High-energy particle collisions at the Large Hadron Collider probe energy scales where emergent effects might become apparent. Astronomical observations of the most distant and energetic objects in the universe might reveal deviations from simple speed of light propagation. The emergence hypothesis also has philosophical implications that extend far beyond physics. If the speed of light is emergent rather than fundamental, it suggests that our entire framework for understanding space, time, and causality might be approximate rather than exact. The laws of physics that seem so solid and universal might actually be effective descriptions that apply only under certain conditions. This doesn't mean that physics is wrong or unreliable. Emergent laws can be just as precise and predictive as fundamental laws within their domains of applicability. The laws of thermodynamics emerge from statistical mechanics, but they're still incredibly useful for understanding engines, refrigerators, and biological systems. Similarly, an emergent speed of light could still serve as a reliable foundation for physics, while pointing toward deeper underlying principles. The search for signs of emergence in the speed of light is part of a broader effort to understand the ultimate nature of physical law. Are the constants we observe in nature fundamental features of reality, or are they emergent properties of more basic processes? Are space and time fundamental aspects of the universe, or do they arise from information, computation, or other more primitive concepts? These questions push physics toward its deepest frontiers, where the distinction between science and philosophy becomes increasingly blurred. They force us to question our most basic assumptions about the nature of reality and to consider possibilities that stretch the boundaries of current understanding. Whether the speed of light is fundamental or emergent, it continues to serve as a guide toward deeper truths about the universe. If it's fundamental, understanding why it has the value it does might reveal profound principles about the mathematical structure of reality. If it's emergent, understanding what it emerges from might lead to revolutionary new theories that unify quantum mechanics, gravity, and information theory. Either way, the speed of light remains one of the most important clues we have about the ultimate nature of existence. It connects space and time, matter and energy, information and causality in ways that continue to surprise and inspire physicists. Whether it represents the deepest level of reality or points towards something even more fundamental, it remains a central piece in humanity's ongoing effort to understand the cosmos and our place within it. Imagine you're falling toward a black hole. As you approach the point of no return, something strange happens to your perception of reality itself. Light from the outside universe becomes increasingly redshifted and distorted. The stars behind you appear to speed up their evolution, racing through millions of years in moments. And then, as you cross the event horizon, the outside universe effectively ceases to exist from your perspective. You've crossed a boundary defined entirely by the speed of light, a boundary that divides reality into regions that can and cannot communicate with each other. This isn't science fiction. It's a direct consequence of the fact that light travels at a finite speed. The speed of light doesn't just set a limit on how fast things can move, it defines the very structure of causality and determines which events can influence each other. In doing so, it creates horizons, boundaries beyond which information cannot travel, and these horizons shape the fundamental nature of observable reality. The most famous of these horizons is the event horizon of a black hole. When a massive star collapses under its own gravity, it can form a region of space-time so severely curved that nothing, not even light, can escape once it crosses a certain boundary. This boundary is the event horizon, and its size is determined entirely by the balance between the object's gravitational pull and the speed of light. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. This radius, called the Schwarzschild radius, is directly proportional to the mass of the black hole and inversely related to the square of the speed of light. If light traveled infinitely fast, black holes couldn't exist because nothing could prevent light from escaping any gravitational field. If light traveled more slowly, black holes would be larger and more common. But the event horizon isn't just a theoretical boundary. It has profound physical consequences that reveal deep connections between gravity, quantum mechanics, and information theory. Stephen Hawking's greatest discovery was that black holes aren't completely black. They emit thermal radiation, now called Hawking radiation, at a temperature that depends inversely on their mass. This radiation emerges from quantum fluctuations near the event horizon. In quantum mechanics, even empty space is filled with virtual particle pairs that briefly pop into existence and then annihilate each other. Near a black hole's event horizon, sometimes one member of such a pair falls into the black hole while the other escapes, becoming real radiation that carries energy away from the black hole. The temperature of this Hawking radiation is incredibly low for stellar mass black holes, about 1/10,000,000th of a degree above absolute zero for a black hole with the Sun's mass. But the radiation exists, and it means that black holes slowly evaporate over time. The bigger the black hole, the lower its temperature, and the slower it evaporates. A black hole with the Sun's mass would take longer than 10 to the 67th years to evaporate completely, vastly longer than the current age of the universe. This evaporation process creates one of the deepest puzzles in modern physics, the black hole information paradox. When matter falls into a black hole, it carries information about its quantum state. But Hawking radiation appears to be purely thermal, carrying no information about what fell into the black hole. If the black hole eventually evaporates completely, where does the information go? Quantum mechanics says that information cannot be destroyed, but general relativity seems to say that information falling into a black hole is lost forever when the black hole evaporates. This apparent contradiction has driven decades of research into the fundamental nature of space-time, gravity, and quantum mechanics. Recent developments suggest that the information might be preserved in subtle correlations in the Hawking radiation, encoded in ways that become apparent only when you consider the quantum entanglement between particles inside and outside the black hole. But understanding exactly how this works requires new insights into the relationship between gravity and quantum mechanics that we don't yet possess. The event horizon creates another puzzling phenomenon: the black hole complementarity principle. From the perspective of someone falling into a black hole, nothing special happens when they cross the event horizon. They continue falling normally until they eventually reach the central singularity where tidal forces tear them apart. But from the perspective of someone watching from outside, the infalling person never actually crosses the horizon. Due to gravitational time dilation, clocks run slower in stronger gravitational fields. As the falling person approaches the event horizon, their clocks appear to run increasingly slowly, as seen by the outside observer. Light from the falling person becomes increasingly redshifted and dimmed. From the outside perspective, the person appears to freeze just above the event horizon, their image fading away as their light redshifts beyond detection. These two descriptions seem contradictory, but both are correct within their respective reference frames. The resolution lies in recognizing that the event horizon is not a physical surface, but rather a boundary in space-time that different observers define differently. The speed of light creates a fundamental limitation on what any single observer can know about distant events. Black holes aren't the only objects that create horizons. Our universe itself has a horizon, called the cosmological horizon, that arises from the expansion of space combined with the finite speed of light. Light from the most distant galaxies has been traveling toward us for billions of years, but there are regions of space so far away that light from them has not had time to reach us since the Big Bang. The observable universe has a radius of about 46 billion light-years, even though the universe is only 13.8 billion years old. This apparent paradox arises because space itself has been expanding during the time it took light to reach us. Light that we see today from the most distant galaxies was emitted when those galaxies were much closer to us than they are now. But even this cosmological horizon is not fixed. As time passes, we can see light from galaxies that were previously beyond our horizon. However, the accelerating expansion of the universe, driven by dark energy, means that there are galaxies we can see today whose light will never reach future observers if the acceleration continues indefinitely. This creates an event horizon for the universe as a whole, similar to the event horizon of a black hole. Future civilizations, trillions of years from now, will live in a cosmos where only nearby galaxies are visible. The cosmic microwave background radiation will have redshifted beyond detection, and nearly all evidence of the Big Bang will have disappeared beyond their horizon. The concept of horizons extends beyond cosmology into the quantum realm. In quantum field theory, accelerated observers experience something called the Unruh effect, where the vacuum of space-time appears to be filled with thermal radiation. An observer undergoing constant acceleration sees a horizon behind them, beyond which no signals can reach them, and this horizon radiates particles at a temperature proportional to their acceleration. This deep connection between acceleration, horizons, and thermal radiation suggests fundamental relationships between gravity, quantum mechanics, and thermodynamics. The laws of black hole thermodynamics, discovered by Jacob Bekenstein and Stephen Hawking, show that black holes have entropy proportional to the area of their event horizons, not their volumes as you might expect. This area law for entropy implies that the information content of any region of space is limited by the area of its boundary, not its volume. This is the holographic principle, which suggests that all the physics inside a volume of space can be encoded on its two-dimensional boundary. The speed of light plays a crucial role in this encoding, determining how information can be distributed across the holographic surface. The holographic principle has led to remarkable insights into the nature of space-time and gravity. The ADS-CFT correspondence, discovered by Juan Maldacena, shows that gravity in a higher dimensional space can be equivalent to a quantum field theory on the boundary of that space. In this correspondence, the speed of light in the higher dimensional space emerges from the properties of the boundary theory. These developments suggest that our three-dimensional experience of space might be a holographic projection of information stored on a two-dimensional surface. If so, the speed of light might not be a fundamental property of space, but rather a consequence of how information is processed and transmitted in the holographic encoding. Horizons also play crucial roles in our understanding of the early universe. During cosmic inflation, regions of space that are now separated by vast distances were once in causal contact. The nearly uniform temperature of the cosmic microwave background can be explained by this early causal connection, even though these regions are now beyond each other's horizons. The inflationary horizon provides a solution to several cosmological puzzles, but it also creates new questions about the nature of spacetime and causality. If space can expand faster than light during inflation, what determines the speed limit for spacetime expansion? How do quantum fields behave when spacetime itself is changing rapidly? These questions push us toward new theories of quantum gravity and cosmology. De Sitter space, which describes a universe with a cosmological constant like our own, has a peculiar horizon structure. In De Sitter space, every observer has a cosmological horizon, beyond which they cannot receive signals. This creates a finite observable universe for each observer, even though the space itself might be infinite. The De Sitter horizon also radiates thermal radiation, similar to black hole horizons. This radiation, called Hawking De Sitter radiation, has a temperature determined by the cosmological constant and the speed of light. If our universe continues to accelerate indefinitely, future observers will live in a thermal bath of this horizon radiation. The study of horizons has revealed deep connections between gravity, thermodynamics, and information theory that were completely unexpected when Einstein first formulated general relativity. These connections suggest that space, time, and gravity might emerge from more fundamental information theoretic processes, with the speed of light playing a central role in determining how information is stored and transmitted. Causal horizons also impose fundamental limits on computation and information processing. The Bekenstein bound states that the maximum amount of information that can be stored in any region of space is proportional to the area of its boundary and the energy contained within it. This bound emerges directly from combining quantum mechanics, general relativity, and thermodynamics. The speed of light sets the ultimate limit on how fast information can be transmitted between different parts of a computational system. This creates fundamental constraints on the speed and efficiency of any possible computer, whether biological, electronic, or quantum. Even hypothetical computers that harness the energy of entire stars or black holes are limited by the speed of light and the causal structure it creates. These limitations have profound implications for the future of intelligence and computation in the universe. As the universe continues to expand and cool, the amount of computation that can be performed with a given amount of energy decreases. The accelerating expansion driven by dark energy will eventually isolate different regions of space, preventing communication between them and limiting the growth of intelligence. Some physicists have speculated about ways to circumvent these limitations. Proposals include creating artificial black holes to access their computational resources, engineering wormholes to enable faster-than-light communication, or manipulating the vacuum energy to alter the local speed of light. But all of these proposals face enormous theoretical and practical challenges. The speed of light doesn't just set limits on what we can observe or compute, it defines the very concept of simultaneity and causality. Events that are simultaneous for one observer may not be simultaneous for another observer moving at high speed relative to the first. The ordering of cause and effect can be different for different observers, as long as no information travels faster than light. This relativity of simultaneity means that there is no universal now that applies throughout the universe. The present moment is defined differently for each observer, and these different definitions can only be reconciled by respecting the speed of light as the ultimate speed limit for information transfer. Near the boundaries imposed by the speed of light, the familiar concepts of space, time, and causality begin to break down. The closer we get to these boundaries, the more we realize that our everyday intuitions about reality are incomplete. The speed of light doesn't just describe how fast light travels, it reveals the fundamental structure of existence itself. This structure suggests that reality is not made of things moving through space and time, but rather of information and relationships, encoded in patterns that respect the causal limitations imposed by the speed of light. Understanding these patterns and their implications continues to drive research into the deepest questions about the nature of existence, consciousness, and the ultimate fate of intelligence in the universe. What if the speed of light isn't really about light at all? What if it's actually the speed of information itself, the fundamental rate at which the universe processes data and updates its state? This radical perspective emerges from one of the most profound developments in modern physics: the realization that information, not matter or energy, might be the most fundamental constituent of reality. The connection between information and the speed of light begins with a simple but profound observation. Nothing can carry information faster than light travels in vacuum. This isn't just a practical limitation of our technology, it's a fundamental principle that underlies the structure of causality itself. Events can only influence each other if information about them can travel between their locations, and that information is limited by the cosmic speed limit. Consider what happens when you flip a light switch. The electrical signal that carries information about your action travels through the wires at a significant fraction of the speed of light, but never exceeds it. The light that emerges from the bulb carries information about the switch's state to your eyes at exactly the speed of light. Even the quantum mechanical interactions between electrons in the switch operate through virtual photons that respect relativistic constraints. This fundamental connection between information and light speed becomes even more striking when we consider how modern technology actually works. Every computer, every smartphone, every GPS satellite depends on manipulating and transmitting information at speeds governed by the speed of light. The internet itself is fundamentally limited by light speed, which is why there's always a minimum delay when communicating with servers on the other side of the world. But the relationship goes much deeper than technology. In quantum mechanics, information takes on an almost mystical quality. The quantum state of a particle encodes information about its properties, but this information can't be copied exactly, transmitted instantaneously, or observed without disturbing the system. The quantum mechanical limits on information processing are intimately connected to the speed of light through the principles of relativity. The no-cloning theorem in quantum mechanics states that you cannot create an identical copy of an arbitrary quantum state. This isn't just a practical limitation, it's a fundamental principle that prevents certain types of information processing that would otherwise violate relativity. If you could clone quantum states perfectly, you could potentially use quantum entanglement to send information faster than light, violating causality. Similarly, the quantum no-communication theorem shows that quantum entanglement, despite its spooky action at a distance, cannot be used to transmit information faster than light. Even though measuring one entangled particle instantly affects its partner regardless of the distance between them, this effect cannot be used to send signals because the measurement results appear random to each local observer. These quantum information constraints are deeply connected to the speed of light through the structure of space-time itself. In relativistic quantum field theory, the requirement that measurements at space-like separated events cannot influence each other is enforced by commutation relations that depend explicitly on the speed of light. The speed of light isn't just a speed limit for particles, it's a speed limit for information itself. This insight has led to a revolutionary way of thinking about entropy, the measure of disorder or missing information in a system. In classical thermodynamics, entropy seemed like a purely thermal concept related to heat and temperature. But Claude Shannon's work on information theory in the 1940s revealed that entropy is fundamentally about information, measuring how much information is needed to specify the exact state of a system. The connection between thermodynamic entropy and information entropy isn't just an analogy, it's an exact mathematical relationship. Ludwig Boltzmann's famous formula, S equals K log W, where S is entropy, K K is Boltzmann's constant and W is the number of possible microscopic states, is actually a statement about information. The entropy of a system is proportional to the amount of information needed to specify which of its possible microscopic states it's actually in. This information-theoretic view of entropy becomes particularly powerful when combined with relativity and the speed of light. Jacob Bekenstein realized in the 1970s that black holes must have entropy, and that this entropy should be proportional to the area of the black hole's event horizon, not its volume. This was a shocking result because it implied that the amount of information that could be stored in any region of space was limited by the area of its boundary. The Bekenstein bound states that the maximum entropy that can be contained in any region is proportional to the area of the region's boundary divided by 4 times the Planck area, where the Planck area depends on the speed of light, Planck's constant, and Newton's gravitational constant. This bound applies to any region of space, not just black holes, and it represents a fundamental limit on information storage in the universe. But why should the information capacity of a region depend on its boundary area rather than its volume? The answer lies in the holographic principle, which suggests that all the information in a volume of space can be encoded on its 2-dimensional boundary. This principle emerged from studying black holes, but it appears to apply much more generally, possibly to the entire universe. The holographic principle implies that our 3-dimensional experience of reality might be a projection of information stored on a 2-dimensional surface, like a cosmic hologram. In this view, the speed of light plays a crucial role in determining how information is encoded and transmitted across the holographic surface. The apparent 3-dimensional motion of particles might really be patterns of information flow on the 2-dimensional boundary. This holographic description of reality has been made precise in certain theoretical contexts through the ADS-CFT correspondence discovered by Juan Maldacena. This correspondence shows that gravity in a curved spacetime can be exactly equivalent to a quantum field theory without gravity living on the boundary of that spacetime. The speed of light in the gravitational theory emerges from the information processing properties of the boundary theory. In the ADS-CFT correspondence, black holes in the gravitational theory correspond to thermal states in the boundary theory. The Hawking radiation emitted by black holes corresponds to thermal fluctuations in the boundary system. The event horizon, which seems like a fundamental feature of spacetime geometry, emerges from the entanglement structure of information in the boundary theory. This correspondence suggests that spacetime itself, including the speed of light, might be emergent phenomena that arise from more fundamental information theoretic processes. Space and time might not be the stage on which physics happens, but rather patterns in the flow and processing of quantum information. The emergence of space-time from information becomes even more intriguing when we consider quantum error correction. In quantum computing, error correction codes are used to protect quantum information from decoherence and noise. Recent research has shown that the ADS-CFT correspondence can be understood as a kind of quantum error correction code, where the boundary theory encodes information redundantly across multiple degrees of freedom. In this view, the bulk spacetime serves as an error-corrected encoding of information stored on the boundary. The speed of light emerges as a consequence of how this error correction operates, determining the rate at which information can be reliably transmitted through the emergent spacetime. Violations of the speed of light would correspond to errors in the quantum code that would be corrected by the underlying information processing system. This perspective on space-time and the speed of light connects to deep questions about the nature of time itself. In quantum mechanics, time evolution is fundamentally about information processing. The Schrödinger equation describes how quantum information evolves, and the speed of this evolution is constrained by the energy available to the system. The connection between energy and time evolution is made precise by the time-energy uncertainty principle, which states that the uncertainty in energy times the uncertainty in time must be greater than Planck's constant divided by 2. This relationship implies that higher energy processes can happen faster, but there are fundamental limits on how quickly information can be processed, even with unlimited energy. These limits are ultimately related to the speed of light through the relativistic relationship between energy and momentum. Even in quantum mechanics, the speed of information processing is constrained by relativistic causality. The speed of light doesn't just limit the speed of particles, it limits the speed of computation itself. This computational view of physics has led to speculation that the universe itself might be a kind of computer, processing information at the fundamental level to generate the phenomena we observe. In this picture, particles and forces would be like software running on the cosmic computer, with the speed of light representing the clock speed of the underlying hardware. Some physicists have taken this idea literally, proposing that the universe is actually a digital computer running a simulation of reality. Others interpret it more metaphorically, suggesting that computational concepts provide useful ways to think about physical processes without necessarily implying that the universe is literally computational. Either way, the computational perspective highlights the central role of information in modern physics. The laws of physics can be understood as rules for processing information, and the speed of light can be understood as a fundamental constraint on information flow. This constraint shapes everything from the structure of atoms to the evolution of the cosmos. The information theoretic view of physics also provides new insights into the arrow of time. In classical mechanics, the laws of physics are time reversible, meaning that if you could reverse the motion of every particle in the universe, time would appear to run backwards. But in practice, we never see such reversals because they would require perfect knowledge and control of every particle's state. The second law of thermodynamics states that entropy always increases in isolated systems, providing an arrow of time that distinguishes past from future. But this law is statistical rather than fundamental, emerging from the fact that there are many more high entropy states than low entropy states. The universe started in a low entropy state and has been evolving toward higher entropy ever since. This thermal arrow of time is closely connected to the information theoretic arrow of time. As the universe evolves, information becomes increasingly scrambled and difficult to retrieve. The process of scrambling information is fundamentally limited by the speed of light, which determines how quickly correlations can spread through space. Recent research has shown that black holes are the fastest scramblers of information in the universe, mixing up quantum information at a rate that approaches the fundamental limits set by quantum mechanics and relativity. This scrambling rate depends on the black hole's temperature, which is inversely related to its mass and directly related to its surface gravity and the speed of light. The scrambling of information by black holes provides a concrete example of how the speed of light governs information processing in extreme gravitational environments. The time it takes for information to become scrambled is related to the light crossing time of the black hole, reinforcing the connection between geometry, causality, and information. These developments point toward a unified understanding of physics in which information, rather than matter or energy, is the fundamental constituent of reality. In this view, matter and energy are patterns of information. Space and time are structures that organize information processing. And the speed of light is the fundamental rate at which information can flow through these structures. This information theoretic revolution in physics is still ongoing, with new discoveries constantly revealing deeper connections between information, quantum mechanics, gravity, and cosmology. The speed of light, which started as a simple measurement of how fast light travels, has become a central character in this story, connecting the microscopic world of quantum information to the macroscopic structure of space-time. Whether information is truly fundamental or whether it emerges from even deeper principles remains an open question. But the central role of information in modern physics suggests that understanding the nature of information itself might be the key to understanding the deepest mysteries of existence. The speed of light as the ultimate speed limit for information transmission, continues to guide us toward these fundamental truths about the nature of reality. The implications extend far beyond physics into questions about consciousness, computation, and the future of intelligence in the universe. If reality is fundamentally informational, then consciousness might be understood as a particular pattern of information processing, and intelligence might be subject to the same fundamental limits that govern physical processes. The speed of light, in this view, doesn't just limit how fast we can travel or communicate. It limits how fast we can think and how quickly intelligence can grow and spread throughout the universe. Understanding these limits and their implications might be crucial for the long-term survival and development of intelligent life in an information-based cosmos. Everything you've ever seen, every measurement you've ever made, every scientific instrument that has ever been built depends entirely on light. This isn't just a practical limitation, it's a fundamental constraint that shapes our entire understanding of reality. We are, quite literally, prisoners of light, and this imprisonment might be creating illusions about the very nature of the universe. Consider the simple act of reading these words. Light from your screen or from the page enters your eyes, triggering chemical reactions in your retina that send electrical signals to your brain. Your entire visual experience is mediated by electromagnetic radiation, traveling at exactly 299,792,458 meters per second. You have no direct access to the objects you're observing, only to the light that has interacted with them. This dependence on light creates a kind of circular reasoning that permeates all of physics. We use light to study light. We use electromagnetic instruments to measure electromagnetic phenomena. We use theories based on the speed of light to interpret observations that depend on the speed of light. It's like trying to measure the length of a ruler using only that same ruler. The circularity becomes even more profound when we realize that all of our fundamental measuring instruments are essentially light detectors. Atomic clocks measure time by counting the oscillations of electromagnetic transitions in atoms. Laser interferometers measure distance by comparing the phases of light waves. Even our most sophisticated particle detectors work by observing the light or other electromagnetic radiation produced when high-energy particles interact with matter. This means that any variation in the speed of light would be nearly impossible to detect using conventional methods. If light suddenly started traveling twice as fast everywhere in the universe, our clocks would run differently, our rulers would measure differently, and all of our calibrated instruments would read differently in ways that would exactly compensate for the change. We might never notice that anything had changed at all, but the problem goes deeper than just measurement. Our entire conceptual framework for understanding space and time is built around the assumption that light travels at a constant speed. The meter is defined as the distance light travels in a specific fraction of a second. Time intervals are measured by counting electromagnetic oscillations. Even our concept of simultaneity, the idea that events can happen at the same time, depends on the assumption that we can synchronize distant clocks using light signals. This creates what philosophers call the problem of empirical equivalence. If we changed the speed of light, but also changed all of our measuring instruments in exactly the right way, the two scenarios would be completely indistinguishable from our perspective. We would have no way to tell which scenario was real, because all of our evidence would be filtered through tools that themselves depend on the speed of light. The situation becomes even stranger when we consider relativity. According to Einstein's theory, observers moving at different speeds will disagree about the timing and ordering of events, the lengths of objects, and the rate at which clocks tick. But they will all agree on the speed of light in vacuum. This agreement isn't because light has some special property that makes it travel at the same speed for everyone. It's because space and time themselves adjust to make it appear that way. From this perspective, the constancy of light's speed isn't a fact about light. It's a fact about how we measure space and time. Light appears to travel at a constant speed because we've chosen to define our units of measurement in a way that makes it constant. It's like choosing to measure all distances in units of wavelengths of a particular color of light, then being surprised that the wavelength always measures exactly 1 unit. This raises profound questions about the nature of physical law. Are the constants we observe in nature real features of the universe, or are they artifacts of how we choose to measure things? If we use different measurement standards, would the universe appear to have different fundamental constants? And if so, which set of constants, if any, represents the true nature of reality? The problem becomes acute when we consider the history of measurement standards. For most of human history, units of length were based on parts of the human body: the foot, the cubit, the span. These units varied from person to person and culture to culture, making it clear that they were arbitrary human conventions rather than natural constants. The move toward universal measurement standards seemed to solve this problem by grounding units in apparently objective natural phenomena. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. The second was defined as a fraction of the solar day. These definitions seem to connect human measurements to universal natural constants, but even these natural standards turned out to be more arbitrary than they appeared. The Earth's circumference isn't perfectly constant, and the length of a day varies due to tidal forces and other effects. More fundamentally, there's no obvious reason why Earth's size or rotation period should be privileged over those of any other planet. The current definition of the meter in terms of the speed of light appears to solve these problems by grounding measurement in a truly universal constant. But this solution creates the circular reasoning we've been discussing. We define distance in terms of light speed, then use distance measurements to study light, then conclude that light speed is constant. The logic is unbreakably circular. This circularity isn't necessarily a flaw in science, but it does reveal important limitations in what we can know about the universe. We can never step outside our own measuring apparatus to get an objective view of what we're measuring. All of our knowledge is necessarily filtered through instruments that themselves embody assumptions about the nature of reality. The situation is reminiscent of Plato's allegory of the cave, where prisoners chained in a cave mistake shadows on the wall for reality itself. We might be like those prisoners, mistaking the patterns of light that reach our instruments for the underlying reality that creates those patterns. The true nature of space, time, and the speed of light might be forever hidden behind the veil of our light-based observations. But the analogy isn't perfect, because unlike Plato's prisoners, we can't escape our cave to see reality directly. There's no view from outside the universe that would allow us to observe it without using light or other electromagnetic phenomena. Even our most abstract theories are ultimately grounded in observations that depend on electromagnetic interactions. This epistemic limitation becomes particularly important when we consider cosmology and our attempts to understand the universe as a whole. All of our information about distant galaxies comes from light that has traveled billions of years to reach us. We're seeing these galaxies as they were in the distant past, not as they are now. Our entire picture of cosmic evolution is based on assumptions about how light behaves over cosmic distances and timescales. If the speed of light varied over cosmic time, or if it behaved differently in different regions of space, our interpretation of astronomical observations could be completely wrong. A galaxy that appears to be 10 billion light-years away might actually be much closer or much farther, with the apparent distance being an artifact of how light traveled through intervening space. The cosmic microwave background radiation, often called the afterglow of the Big Bang, provides our most detailed picture of the early universe. But this picture is entirely based on electromagnetic radiation that has been traveling through space for over 13 billion years. Any changes in how this radiation propagated during its journey would fundamentally alter our understanding of cosmic history. Recent observations suggesting that the expansion of the universe is accelerating are based on measurements of distant supernovae using their apparent brightness compared to their expected intrinsic brightness. But these measurements assume that light from the supernovae traveled through space at a constant speed and wasn't affected by unknown physical processes during its billion-year journey to Earth. The discovery of dark energy, which is thought to drive this cosmic acceleration, might actually be an artifact of incorrect assumptions about light propagation. If light loses energy as it travels through space due to interactions with virtual particles or other quantum effects, distant supernova would appear dimmer than expected, mimicking the effects of accelerated expansion. Even our understanding of stellar evolution and the age of stars depends on assumptions about how light is produced in stellar cores and how it travels through stellar atmospheres. The nuclear fusion processes that power stars are understood through quantum mechanics and nuclear physics, both of which are calibrated using terrestrial experiments that depend on electromagnetic measurements. The problem extends to particle physics and our understanding of fundamental particles. All of our knowledge about quarks, leptons, and force-carrying particles comes from high-energy collision experiments, where we infer the properties of particles from the electromagnetic signals they produce when they interact with detectors. We've never directly observed a quark or a neutrino, only the patterns of light and electrical signals they create. Even more fundamentally, our entire mathematical framework for describing physics is built around concepts that emerged from our electromagnetic experience of the world. Our notions of space and time, continuity and discreteness, symmetry and conservation, all arose from observations that were ultimately based on electromagnetic interactions. The mathematics of calculus, which underlies all of modern physics, was developed to describe smooth, continuous motion of the sort that we observe in electromagnetic phenomena. But if space and time are actually discrete at the smallest scales, or if they have some other structure that's hidden by our electromagnetic observations, then our mathematical tools might be fundamentally inadequate for describing reality. Quantum mechanics itself might be an artifact of how electromagnetic measurements work rather than a fundamental description of reality. The wave function, which is central to quantum mechanics, describes probability amplitudes for measurement outcomes. But these measurements are almost always electromagnetic in nature, involving photons interacting with charged particles or magnetic fields. The famous measurement problem in quantum mechanics, which asks why measurements seem to collapse wave functions while evolution between measurements is smooth and deterministic, might be an artifact of the electromagnetic nature of measurement itself. If we could somehow observe quantum systems without using electromagnetic interactions, they might behave very differently than our current theories predict. The uncertainty principle, which limits how precisely we can simultaneously measure complementary properties like position and momentum, emerges partly from the electromagnetic nature of measurement. To measure the position of a particle precisely, we need to use high-energy photons with short wavelengths. But these photons carry momentum that they transfer to the particle, disturbing its motion and making momentum measurements less precise. If we could observe particles without using electromagnetic interactions, the uncertainty principle might not apply in the same way. The fundamental limits it represents might be limits on electromagnetic observation, rather than limits on the nature of reality itself. This possibility connects to deeper questions about the relationship between consciousness and measurement in quantum mechanics. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in collapsing wave functions and determining measurement outcomes. But if measurement is always electromagnetic, then what we call consciousness might really be a particular pattern of electromagnetic activity in brains. The hard problem of consciousness, which asks how subjective experience arises from objective physical processes, might be intimately connected to the electromagnetic nature of neural activity. Our brains are essentially electromagnetic computers, processing information through electrical signals and chemical reactions that are ultimately governed by electromagnetic forces. If consciousness emerges from electromagnetic processes, then our understanding of consciousness is necessarily limited by the same constraints that limit our understanding of electromagnetic phenomena. We might be trapped not just in an electromagnetic cave when it comes to observing the external world, but also when it comes to understanding our own minds. The anthropic principle in cosmology suggests that the fundamental constants of nature must be compatible with the existence of intelligent observers like ourselves. But if intelligence itself depends on electromagnetic processes, then the anthropic principle might be selecting for universes where electromagnetic phenomena behave in ways that support the existence of electromagnetic-based intelligence. This creates a kind of observational selection effect, where we can only exist in universes where the speed of light and other electromagnetic constants have values that allow for the existence of electromagnetic-based measurement apparatus and electromagnetic-based intelligence. Universes with different values of these constants might exist, but contain no observers capable of studying them. The illusion of constancy in the speed of light might therefore be a fundamental feature of any universe capable of supporting electromagnetic-based observers. We see the speed of light as constant, not because it really is constant, but because we can only exist in universes where it appears constant to electromagnetic-based measuring devices. This perspective suggests that many of the constants and laws we observe in physics might be more about the constraints on observation and intelligence than about the fundamental nature of reality. The universe might be much stranger and more varied than it appears to our electromagnetic senses, but those strange aspects remain forever hidden behind the veil of electromagnetic measurement. The recognition of these limitations doesn't invalidate science, but it does humble our claims about what science can tell us about ultimate reality. Science reveals the patterns and relationships that are accessible to electromagnetic observation, but it might be silent about aspects of reality that exist beyond the reach of electromagnetic interactions. Understanding these limitations might actually point toward new possibilities for extending our knowledge. By recognizing that our current understanding is constrained by our dependence on electromagnetic phenomena, we might be able to imagine new ways of probing reality that go beyond these constraints, or at least to better understand what aspects of our current theories reflect real features of the universe versus artifacts of our measurement methods. As we stand at the edge of the 21st century's third decade, the speed of light remains both our most precisely known constant and our deepest mystery. Every new experiment designed to test its constancy, every theoretical breakthrough that questions its fundamentality, every technological advance that pushes the boundaries of measurement, brings us face to face with the same profound question. Are we approaching a final understanding of this cosmic speed limit, or are we about to discover that everything we think we know is just the beginning? The future of light speed research lies at the intersection of humanity's most ambitious scientific endeavors. Deep underground, gravitational wave detectors like LIGO and Virgo are becoming so sensitive that they can measure distortions in spacetime smaller than 1/10,000th the width of a proton. These instruments don't just detect gravitational waves, they probe the very fabric of spacetime itself, testing whether the speed of light remains constant under the most extreme conditions the universe can produce. Future gravitational wave detectors will be even more ambitious. The Laser Interferometer Space Antenna, LISA, will consist of 3 spacecraft flying in formation millions of kilometers apart, using laser beams to detect gravitational waves from across the cosmos. This space-based detector will be sensitive to gravitational waves that last for months or years, allowing scientists to watch massive black holes merge in slow motion and test whether the speed of light varies over cosmic timescales. But gravitational wave astronomy is just one front in the battle to understand light's ultimate nature. High-energy particle accelerators are pushing toward energies where the familiar smooth space-time of Einstein's theory might break down into something more fundamental. At the Large Hadron Collider, protons collide at energies of 13 trillion electron volts, creating conditions that haven't existed since the first moments after the Big Bang. Future accelerators will reach even higher energies, approaching the Planck scale, where quantum effects of gravity become important. At these energies, the speed of light might not be the simple constant we observe at low energies. Instead, it might emerge from more fundamental processes, just as the speed of sound emerges from molecular motion in gases and liquids. The International Linear Collider, if built, will accelerate electrons and positrons to nearly the speed of light and smash them together with unprecedented precision. These collisions will probe the structure of space-time at the smallest scales accessible to human technology, searching for signs that space and time themselves might be made of discrete units rather than the smooth continuum that Einstein envisioned. Even more exotic experiments are being planned to test the very foundations of relativity. Some scientists are designing laboratory tests of whether empty space itself might have electromagnetic properties that could affect light propagation. Others are looking for tiny violations of Lorentz invariance, the principle that the laws of physics are the same for all observers moving at constant speeds. The European Space Agency's microscope mission has already tested the equivalence principle, which states that gravitational and inertial mass are identical to unprecedented precision in the weightless environment of space. Future missions will extend these tests to even higher precision, looking for any sign that Einstein's theory of general relativity might break down under extreme conditions. But perhaps the most revolutionary experiments are happening in quantum laboratories around the world, where scientists are learning to manipulate individual photons and atoms with exquisite precision. These quantum experiments are revealing aspects of light's behavior that challenge our most basic assumptions about the relationship between information, measurement, and reality. Quantum teleportation experiments have successfully transmitted the quantum state of photons across distances of hundreds of kilometers. These experiments don't violate the speed of light limit because no information actually travels between the source and destination. Instead, the quantum state is destroyed at the source and recreated at the destination using previously shared quantum entanglement. But future quantum experiments might push this boundary even further. Scientists are working toward quantum networks that would link quantum computers around the world, creating a quantum internet that could process certain types of information in ways that seem to transcend classical limitations. While these networks would still respect the speed of light for classical communication, they might reveal new aspects of how information itself behaves at the quantum level. The search for dark matter and dark energy is also opening new windows into the nature of light and space-time. Dark matter appears to interact gravitationally, but not electromagnetically, suggesting that there might be entire sectors of physics that are invisible to light-based observations. Future dark matter detectors buried deep underground or launched into space might reveal particles and forces that operate according to different rules than ordinary matter. Dark energy, the mysterious force driving the accelerated expansion of the universe, might be connected to the vacuum energy of space-time itself. If so, understanding dark energy might require us to understand how quantum fields behave in expanding space-time, potentially revealing new aspects of how light propagates through the cosmos. The James Webb Space Telescope and its successors are already revealing galaxies that formed when the universe was less than 1 billion years old. These observations probe cosmic history back to within a few 100 million years of the Big Bang, testing whether the fundamental constants of physics, including the speed of light, have remained truly constant over cosmic time. Future space telescopes will push even further back in time, potentially observing the first stars and galaxies to form in the universe. If the speed of light or other fundamental constants varied in the early universe, these observations might reveal telltale signatures in the cosmic microwave background radiation or in the properties of the most distant objects. Some of the most intriguing possibilities lie in the realm of quantum gravity, where physicists are trying to unify Einstein's theory of general relativity with quantum mechanics. String theory, loop quantum gravity, and other approaches all suggest that space-time itself might have a granular structure at the Planck scale, where our usual concepts of space and time break down. In these theories, the speed of light might emerge as an average property of how information propagates through discrete space-time units, just as the speed of sound emerges from molecular motion. At energies approaching the Planck scale, light might not behave like waves propagating through smooth space-time, but rather like signals being processed by a cosmic computer with discrete time steps and finite memory. Causal set theory proposes that space-time is made of discrete events connected by causal relationships, with the speed of light emerging from the rate at which causal influences can propagate through this network. In this picture, testing the constancy of light's speed at ultra-high energies would be like testing the clock speed of the universe itself. Emergent gravity theories suggest that gravitational force itself might arise from quantum entanglement effects, with space-time curvature being a macroscopic manifestation of quantum information processing. In these theories, the speed of light would be related to the rate at which quantum entanglement can be created and destroyed, connecting the cosmic speed limit to fundamental limits on quantum computation. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, implies that the three-dimensional space-time we experience might be a projection of more fundamental two-dimensional physics. If so, the speed of light in our three-dimensional experience might be an emergent property of information processing on the two-dimensional holographic screen. Advances in quantum computing are also opening new ways to test these ideas. Quantum computers can simulate quantum systems that are too complex to study analytically, potentially allowing scientists to model space-time emergence from quantum entanglement or test how information propagates in discrete space-time models. Quantum error correction, which protects quantum information from decoherence, has revealed deep connections between information theory and space-time geometry. Some researchers believe that space-time itself might be an error-correcting code, with the speed of light emerging from the rate at which quantum errors can be detected and corrected. Artificial intelligence is revolutionizing how we analyze data from physics experiments. Machine learning algorithms can find patterns in gravitational wave signals, particle collision data, and astronomical observations that would be impossible for humans to detect. These tools might reveal subtle variations in fundamental constants that have been hidden in the noise of experimental data. Future AI systems might even help design new experiments to test the constancy of fundamental constants. By analyzing vast databases of theoretical predictions and experimental results, AI could identify the most promising approaches for detecting variations in the speed of light or other fundamental parameters. But perhaps the most profound developments will come from our growing understanding of the relationship between physics and computation. The realization that physical processes can be understood as information processing is leading to new theories where the laws of physics emerge from computational principles rather than being fundamental features of reality. In these computational theories, the speed of light might be related to the maximum rate at which the universe can process information. Just as ordinary computers have clock speeds that limit how fast they can perform calculations, the universe might have a fundamental clock speed that limits how fast physical processes can occur. This computational view of physics connects to deep questions about the nature of time itself. In traditional physics, time is a parameter that describes when events happen. But in computational physics, time might be more like the tick of a cosmic clock, marking discrete steps in the universe's information processing algorithm. If time is discrete rather than continuous, then the speed of light would be measured in distance per time step, rather than distance per continuous time interval. Testing whether time is continuous or discrete would require experiments at the Planck time scale, about 10 to the minus 43 seconds, far beyond current technological capabilities. The search for a theory of quantum gravity continues to drive physics toward new conceptual frameworks that might revolutionize our understanding of the speed of light. Whether these frameworks reveal the speed of light to be truly fundamental or show it to be emergent from deeper processes, they will certainly deepen our understanding of the relationship between space, time, information, and reality. Experimental tests of these theories will require new technologies that push measurement precision to unprecedented levels. Atomic clocks are already precise enough to detect time dilation effects from height differences of just a few centimeters. Future atomic clocks might be sensitive enough to detect gravitational waves directly or to test whether time itself flows at a constant rate. Laser interferometry is approaching fundamental limits imposed by quantum mechanics itself. Future gravitational wave detectors will need to overcome quantum noise using techniques like squeezed light states that reduce quantum uncertainty in some measurements at the cost of increasing it in others. Space-based experiments will become increasingly important as we try to test physics under conditions that can't be replicated on Earth. Experiments in free fall can test the equivalence principle to higher precision. Experiments far from gravitational sources can test whether fundamental constants vary with gravitational field strength. The study of black holes will continue to provide unique laboratories for testing extreme physics. As our ability to observe black holes improves, we might be able to detect subtle deviations from Einstein's predictions that could reveal new physics. The Event Horizon Telescope has already produced the first images of black hole event horizons, and future developments will provide even more detailed pictures. Multi-messenger astronomy, which combines gravitational waves, electromagnetic radiation, and neutrinos from the same sources, is opening new ways to test fundamental physics. When LIGO and Virgo detected gravitational waves from merging neutron stars in 2017, telescopes around the world observed the electromagnetic counterpart, providing unprecedented tests of how different types of radiation propagate through space. Future multi-messenger observations might detect subtle differences in arrival times between gravitational waves and electromagnetic signals that could reveal violations of the speed of light limit. Even tiny differences would be detectable over cosmic distances, providing exquisitely sensitive tests of fundamental physics. But regardless of what these experiments reveal, the speed of light will continue to play a central role in our understanding of reality. Whether it proves to be truly fundamental or emerges from deeper processes, whether it remains perfectly constant or varies in subtle ways, it will continue to guide us toward deeper truths about the nature of existence. The journey to understand light's speed has already transformed our conception of space, time, matter, and energy. It has revealed the intimate connections between seemingly separate phenomena and has shown us that reality is far stranger and more beautiful than anyone could have imagined. As we push toward even deeper understanding, the speed of light remains our most reliable guide into the heart of cosmic mystery. The future may reveal that the speed of light is just one aspect of a more comprehensive theory that unifies all of physics. Or it may show that light speed points toward aspects of reality that transcend physics entirely, connecting to fundamental questions about consciousness, computation, and the nature of existence itself. Either way, the speed of light will continue to illuminate the path toward ultimate understanding. We began this journey with a simple number: 299,792,458 meters per second. We end it with something far more profound. The speed of light isn't just a velocity. It's the thread that weaves together space and time, matter and energy, information and causality, the quantum and the cosmic. It's the speed limit of reality itself. Through the centuries, our understanding of this cosmic constant has evolved from crude estimates based on astronomical observations to precision measurements that push the boundaries of what's possible with human technology. We've gone from Romer's timing of Jupiter's moons to gravitational wave detectors that can sense distortions in space-time smaller than 1,000th the width of a proton. Each measurement has been more precise than the last, yet each has also deepened the mystery rather than resolving it. The speed of light defines the structure of space-time, creating horizons that separate the observable from the unobservable, the knowable from the unknowable. It sets the ultimate limits on causality, ensuring that cause precedes effect and that information cannot travel from the future to influence the past. Without this cosmic speed limit, the universe would collapse into paradox and chaos. But the speed of light is more than just a constraint. It's also an enabler. It makes possible the rich structure of relativity, where space and time dance together in ways that seemed impossible to previous generations. It allows for the existence of stable atoms, the propagation of electromagnetic waves, and the complex chemistry that underlies life itself. A universe without the speed of light, or with a fundamentally different speed, would be unrecognizable. The quantum realm reveals even stranger aspects of light's behavior. Photons exist in superpositions of multiple states, tunnel through barriers that should be impenetrable, and become entangled in ways that seem to transcend space and time. Yet through all this quantum weirdness, they still respect the cosmic speed limit, traveling at exactly the same speed regardless of their energy or the complexity of their quantum state. This constancy in the face of quantum uncertainty points to something deeper than mere coincidence. The speed of light isn't just a property of light. It's a fundamental feature of the information processing capacity of the universe itself. It determines how quickly quantum states can evolve, how fast information can propagate, and how rapidly the universe can update its configuration from one moment to the next. The connection between light speed and information reveals new layers of mystery. If reality is fundamentally informational, as many modern theories suggest, then the speed of light might be the clock speed of cosmic computation. It might determine not just how fast things can move through space, but how fast the universe can think, process, and evolve. This computational view of physics suggests that we might be living inside a kind of cosmic computer, where particles and forces are like software running on quantum hardware. The speed of light would then represent a fundamental limitation of this hardware, determining how quickly it can execute the algorithms that generate the phenomena we observe. But even as we develop these new perspectives, we must remember the limitations inherent in our position as observers. Every measurement we make, every theory we develop, every insight we gain, is filtered through instruments and concepts that themselves depend on electromagnetic phenomena. We are, quite literally, made of atoms held together by electromagnetic forces, observing a universe through the medium of electromagnetic radiation. This creates a kind of epistemological prison from which we can never fully escape. We can never step outside the universe to observe it objectively, never transcend our dependence on electromagnetic interactions, never gain access to absolute truth, independent of our measurement apparatus. The speed of light might appear constant, not because it really is constant, but because any variation would be automatically compensated by changes in our measuring instruments. Yet this limitation doesn't invalidate science or render futile our quest for understanding. Instead, it reveals the remarkable consistency and coherence of the physical world. The fact that we can construct precise theories, make accurate predictions, and build sophisticated technologies based on our electromagnetic observations suggests that there are deep patterns in nature that transcend the details of how we observe them. The speed of light serves as a kind of Rosetta Stone for translating between different aspects of physics. It connects mechanics and electromagnetism, quantum theory and relativity, thermodynamics and information theory, cosmology and particle physics. No other constant plays such a central role in so many different areas of science. This universality suggests that the speed of light might be more than just an empirical constant. It might represent a deep principle about the structure of reality itself, a principle that we're only beginning to understand. Whether it emerges from quantum information processing, from the geometry of higher dimensional spaces, or from some other fundamental process, it clearly reflects something profound about the nature of existence. The debates about whether the speed of light is truly constant, whether it's fundamental or emergent, whether it might have been different in the past or could change in the future, are more than just technical arguments among physicists. They're really debates about the nature of physical law itself. Are the constants of nature eternal and unchanging, or are they dynamic quantities that evolve along with the universe? The answer to this question has profound implications for our understanding of cosmic history and our place within it. If fundamental constants can change, then the universe might be far more dynamic and evolutionary than we currently believe. The laws of physics themselves might be subject to natural selection, with only certain combinations of constants allowing for the emergence of complexity and intelligence. This possibility connects to deep questions about the anthropic principle and the apparent fine-tuning of physical constants for the existence of life. If constants like the speed of light can vary, then we might exist in just one bubble of a vast multiverse, where different regions have different physical laws. Our local physics might be just a small sample of a much larger space of possibilities. Alternatively, the constants might be fixed by deep mathematical principles that we don't yet understand. The speed of light might have the value it does, because that's the only value consistent with the mathematical structure of space-time, quantum mechanics, and the other pillars of modern physics. Understanding these mathematical constraints might be the key to a truly unified theory of everything. The search for such a theory continues to drive physics toward new frontiers. String theory, loop quantum gravity, emergent gravity, and computational theories of physics all offer different perspectives on what might lie beneath the familiar laws of electromagnetism and gravity. Some of these theories suggest that the speed of light emerges from more fundamental processes, while others treat it as truly fundamental. Regardless of which theoretical approach ultimately proves correct, the speed of light will continue to play a central role in our understanding of reality. It provides a bridge between the human scale of everyday experience and the cosmic scale of astronomical phenomena. It connects the instantaneous world of quantum mechanics with the stately evolution of galaxies and black holes. Looking toward the future, new experimental techniques promise to test our understanding of the speed of light under ever more extreme conditions. Gravitational wave astronomy is opening a new window into the nature of space-time itself. Quantum technologies are revealing previously hidden aspects of light's behavior. Space-based experiments are probing fundamental physics in environments that can't be replicated on Earth. These experiments might reveal that the speed of light is truly constant and fundamental, confirming our current understanding and pointing toward even deeper principles. Or they might uncover subtle variations that revolutionize our picture of physics and cosmology. Either outcome would represent a triumph of human curiosity and ingenuity. But perhaps the most important lesson from our exploration of light's speed is not about physics at all, but about the nature of human knowledge itself. The history of measuring and understanding the speed of light is really a history of how science works, how careful observation, creative experimentation, and bold theorizing combine to reveal truths about the natural world that transcend our everyday experience. The speed of light has served as a constant reminder that reality is far stranger and more wonderful than common sense would suggest. It has forced us to abandon comfortable assumptions about absolute time and universal simultaneity. It has revealed connections between space and time, matter and energy, geometry and physics that no one could have anticipated. Most importantly, it has shown us that the universe has a deep, mathematical structure that can be discovered through patient investigation and creative thinking. The fact that we can measure something as elusive as light speed, that we can connect this measurement to profound theories about space and time, and that we can use these theories to make accurate predictions about phenomena from particle accelerators to GPS satellites, demonstrates the remarkable power of scientific reasoning. The speed of light doesn't just illuminate objects in space, it illuminates the path toward understanding itself. It shows us that even the most fundamental aspects of reality are accessible to human investigation, even if that accessibility comes with inherent limitations and unavoidable uncertainties. As we continue to probe deeper into the nature of space-time, quantum mechanics, and cosmic evolution, the speed of light will remain our faithful guide. Whether it leads us to a final theory of everything or reveals new mysteries that push understanding even further, it will continue to serve as a beacon marking the boundary between the known and the unknown. In the end, the speed of light represents something uniquely human: the desire to understand our place in the cosmos. It embodies our refusal to accept ignorance as final, our determination to push beyond the limits of direct experience, and our faith that the universe, however strange it might be, is ultimately comprehensible. Light speed may not merely measure the universe, it may measure the boundaries of what we can ever know. But within those boundaries lies a realm of discovery so vast and rich that it could occupy human minds for millennia to come. The light that guides us toward truth may never reveal everything, but it reveals enough to keep us wondering, questioning, and reaching toward ever deeper understanding of the magnificent cosmos we call home.